This is going to be a more systematic treatment of those curves with level structures. And just let me recall what we did in the last lecture. Well, I tried to convey this message, which there are two blackboards. One is dirty, and the other one is clean. And the clean one was devoted to these beautiful objects called orbifolds, where everything works very nicely. And the dirty one was devoted to those badly behaving things, where still everything is compact. And now let me just say that I'm going to use letters like this for spaces, and letters like this for stacks or orbifolds. I probably call them stacks. And yeah, I don't have it. Well, on the notes, I use the fancy letters even for morphisms. So fancy letters, you know, a fancy F for a morphism here, and then a not very fancy straight F for the corresponding thing. So this may look like a very obvious thing that one can speak about, but actually it only exists for orbifolds or stacks of the Lin-Mumford type. The existence of these maps and spaces, algebraic spaces, has been is a theorem of Peel and Mori. And so I think it feels as if this thing should have a name somewhere in the literature, but it hasn't. It is a functor, right? Transforming stacks to spaces, morphism between stacks to spaces. I propose one in the notes, which is still another joke of Alessio Corti, which I call reification, okay? Because things are here in this word and become concrete things in the underlying word here. There is a nice functor. Anyway, so let's start the actual talk. And let's start speaking, so we get on the clean blackboard, and speak about these fancy curves, which are curves with non-trivial stabilizers at the nodes. I allow myself to consider nodes only if I add to them a cyclic stabilizer. Okay, so I will call them not ordinary stable curves, but ZL stable curves. These are types of twisted curves, as you see them in the literature, and they have been systematically treated by Vistoli, Abramovich and Vistoli, and they also appear in some early writings of Konciewicz. So what are those things? Those are, well, stacks, but very simple stacks of dimension 1, for example, plus with nodal singularities. Meaning that if they are singular, points that are singular can be locally described as xy equals 0 inside C2. And then if you look, so those are things that I write like this, but if I go back to the spaces, then I actually get a nodal curve. And this nodal curve is a stable curve in the ordinary sense. In the sense, if you prefer this, then this is ample. For the time being, I'm not considering markings. So automatically, I'm speaking about genus 2 things. Or we'll see some variants in a minute. But then what I really want to stress is the automorphism group, i.e. the stabilizer at a certain point of the curve, is equal to 1 if P, the point, is smooth, and is equal to the cyclic group of order L otherwise. And I can be more precise about this. The local picture at a node looks like, as you know, xy equals 0, and then I have to act on this by a cyclic group of order L. So here I have a little chart which is a quotient stack. And the action is as follows. Take the pair xy. It goes to we didn't really see that yesterday. We only had minus x and minus y. But in general, that's the structure that you have to put on a node. The reason why things are defined in this way, with this balanced structure at the node, is that those kind of curves can be smoothened. Otherwise, they just stay nodal. And the node persists. You cannot smoothen them. So it's better to just restrict to those. So in the literature, you will see the notion of balanced twisted curves, but we're trying to cut through all this terminology. Just let me introduce a notation. Every time I have an affine space and I'm acting by a cyclic group of order L, I will use this notation, which is obvious, I think. Once you choose a primitive root of unity, this describes exactly what happens here. I mean, the matrix that has on the diagonal, this diagonal matrix, exponent 2 pi I, 1 over L, exponent 2 pi I, L minus 1 over L. Okay, so as I said, what we are really interested in are not these ZL stable curves, but more those curves equipped with a line bundle whose R tensor power is trivial. This is something we can call L level curves. And now, what is surprising is that these have the same definition as in the smooth case. They are simply curves, line bundles, equipped with an isomorphism going from this to this. This is what we called level curves for smooth curves, and we keep on calling level curves here. And if you want to have a portrait, well, just a curve, but recall that those nodes are all of type 1 over L, 1, L minus 1. And now I'm going to install on this curve a line bundle. And okay, let me skip the rest. But what I want to tell you about is what happens at that point. Because now you have two coordinates, right? X and Y, and you know how the group acts there. But I've insisted on the fact that when you define a line bundle on an orbifold, you have to lift the action on the fiber. And that's part of your data. So what if I want to describe the local picture remark at this point here. The local picture is, well, I have again a chart. It looks like xy equals 0 times C, where C is the fiber here. And now I have an action of ZL And how is this action defined? Well, let me use that notation and write simply so this automatically produces an invariant of the node, which I call the multiplicity at the node. And there's naturally an index between 0 and L minus 1. You may notice that I have privileged this branch parameterized by x. And if I had chosen the other one, m would have been changed for the other index, which is congruent to minus m modulo L. Okay? But up to that choice, this is well defined. And so, just as in the case of stable curves, level curves admit a nice dual graph, which I'm going to describe, because it's a dual graph which is decorated with respect to the usual ones. Okay? So we used to associate to this a dual graph with the 2 vertices and 2 edges. Oh, go ahead.
What did you say M was?
The number between 0 and L minus 1 that I can put here and that describes the action of ZL at that point. So if you don't like this notation, you should consider that this notation stands for the coordinate x, the coordinate y, and the coordinate t. Okay, so let me just make it precise. So x, y, and t. T is the coordinate in this direction. Okay? And now I'm going to act on this 3-dimensional space parameterized by x, y, and t by ZL. Okay? So how can you do that? Well, the action turns out to be very simple. It's a matrix like the one we found yesterday when we defined orbifold cohomology. And the little number that I put here is the unique number between 0 and L minus 1 that makes the action work like this. So I have very quickly switched to this notation, which seemed to me more convenient. Okay? Let me recover the eraser. Stop. Which I have squeezed there. And let me bring back the... Oh, it doesn't come back anymore. Oh, no, don't go so far. Okay. So, okay. And it's good to have 2 blackboards, I guess. Okay, so dual graphs. Now, if you look at this curve that we have over there, then the dual graph for you is a graph that has as many nodes, as many vertices as the irreducible components. So 2 vertices. And then it's a graph that has as many edges as the nodes of the curves. So here there is a node, and it joins these 2 irreducible components. So I draw an edge here. And here there is another node that joins this irreducible component to itself. So that's the picture that I have. Okay? These dual graphs have been introduced in the course of last week. But what I'm saying here is that I also have defined some multiplicities at every node by this definition. As long as I set a privileged, an order between the 2 ending points of the vertex, of the edge. So every edge is ordered so that I can define n. If I don't do that, then I have some ambiguity. Okay? Then I have a well-defined one cochain given by the datum of all those multiplicities. This is a one cochain. You know, so graphs such as this may be equipped with one cochain, and here I have a one cochain which takes values in ZL. And you know there is a map between one cochains and, okay, let me call it a one chain. It's the same thing. In this context, I don't have any problem. This is actually more nicely said in terms of one cochain somewhere else, but anyway, so in the notes. But anyway, so here I have a boundary, and what I claim is that the multiplicities I get, it is an exercise. This vanishes. When I look at roots of the trivial bundle, this vanishes. Okay, if you want a useful tool for solving this exercise, let me have a remark. The remark is about something which seems completely unrelated, which are subcurves. Okay, so you see this curve, you can pick a subcurve there, and you can wonder if you can still produce a level structure on that subcurve. That is true, but you have to be careful about it. Okay, so let's consider X inside our curve this, and it's a subcurve. And now naturally I can consider the triple and you know, as I said, I have X and I have its reification, and I have this map going from X to this, which is actually a nice map, universal with respect to all morphisms to algebraic schemes. And now I can consider the push forward of this, which I will denote like so. And I want to know what it is. It's a line bundle to begin with. You know, this is a smooth subcurve. So I get a line bundle. This happens because this morphism is flat, by the way. But anyway, so or accept it as a fact of life. And you know, as every line bundle on a smooth orbifold, you can write expressions like this, where D is a divisor. Now, pushing forward to X is the same as taking the round down of this divisor. And now let me tell you what is D. D is an integer divisor plus, or it has the shape of an integer divisor, plus now you look at all the nodes that lie on X, and you look at their multiplicity. Okay? And then I'm telling you that D has this shape. It is not an integer divisor. It is an integer. A priori, it can be a rational divisor, or a divisor with rational coefficients. In general, on orbifolds, I only require that divisor belong to the sum of points over the number of automorphisms of those points for all points inside X. So this is where I take the divisors, and this is what I get. In fact, this proposition is telling you, this remark is telling you, that the shape of this divisor is as follows. So now, I think using this fact, And the way the round down behaves, the round down is just getting back to the integer divisor. You can actually prove this fact. But anyway, so now you know much more than you used to about level curves. And I think it's time for putting markings on these level curves. So let me bring back down that thing. Yes? I don't choose it. Let me see. Yes, as you pointed out, if I want to make this remark meaningful, I should choose an orientation of the graph which privileges all the branches that lie on my chosen subcurve. So I pick up a subcurve, and that's the branches that I'm going to privilege for making this proposition true. Otherwise, before, I could have said things in a different way, saying that. But at that point, when I said that, you rightly pointed out that there is a word missing. But that's why we have notes, right? Anyway, thank you. So. Okay, so markings. Yeah, here a very pleasant thing happens, and that's the reason why I haven't insisted on markings up to now. Let's make things very simple. Again, here is my C, and here is a smooth one, let's say. But now I want to fix a point here. I call it P. And over this point, I put a stabilizer of order L. Obviously, when I get to the reification, I get a smooth curve just with the marking. And now, the very pleasant thing is that there is only one way to construct an orbifold with that stabilizer at P. There is a unique orbifold C. C is uniquely determined by the position of this point and let's call this P and this P tilde, and the order of the stabilizer. And I can even say more. Let's see what omega C is. Well, let's speak about divisors. I compare this to this, and I have a formula saying that Kc is the pullback via this thing of Kc plus, as I told you, these divisors have a tendency to be rational, not integers. So, P. Okay, so, yeah. Okay? Yes, so this can be seen as a Riemann-Hurwitz applied in the context of orbifolds. So just pretend that Riemann-Hurwitz adapts there, and it does. Then you get this formula. It just tells the ramification is a little bit lighter than it used to be for concrete points. Okay, so actually there is a way to avoid remembering all this stuff, which is the following. Now, some people have spoken, I think, about things called Omegalog. I can do it for both, for the curves and for C. For the curve, this is just the same as tensoring by all marking. In this case, I have only one marking. But in general, let's suppose I give a more general definition. And I have several markings. then that's what Omegalog is, the sheaf of logarithmic differentials. And, well, let's just pretend there are automorphisms. But, you know, in the non-stacky case, there aren't. Now, those things are all equal to 1. But I do this because here I will, so in this case, I can safely say that this is, just by definition, Pi. But in this case, I will do the same thing. Now, as a consequence of this formula, we have this nice formula here. Which you can easily verify. Just so now I go to define mark L level curves, and there is a little surprise because there are still curves with this tacky markings, which behave like there, but I just have restricted to the case of a single one, and then I have a single marking, and then I have L, which is this thing, and now look at the local picture of this thing. I mean, even if you, okay, you may have notes, but what I focus on here is what happened at a point. Happens at a point. So again, I have a little portrait, which I won't complete, of what L is above C. Now, let's first look at the point, the stacky point. So, the local picture here could be written like this. You see, here I'm saying something really elementary, but I'm sticking to my formalism of saying that if I have a representation of order L on a one-dimensional complex space, then I write it like this. And now I want to speak about this point here. And the local picture here is going to be of this shape. This M is what I will call the multiplicity of L at the point P. And there's stuff that is going to happen, sorry, in a second, in the enumerative geometry. Stuff is going to be used in the enumerative geometry in a minute.
Are you requiring that the mark points have non-trivial?
So, right now, oh no, I'm not. Yes. I'm not. Just because I want to set up a formalism where I don't have to change my underlying curve all the time. I know this is slightly unusual, so be prepared that there may be different conventions, but this is just a matter of convention. So we are all still friends. Despite
So what is this M as a thing? Is a number?
Oh, yes, sorry. It's just as a big M before,
Okay.
but determined at every. Okay, so now I have curves with markings. I can put line bundles on them. And what I claim is that I don't need to stick to the notion of roots of the trivial bundle. But with this work that we have done, you can take L roots of whatever line bundle you can think of, whatever canonically defined line bundle you can think of, so to speak. Let me make it precise. So this is, after all, boring maybe, but very useful. Now, whenever someone asks you to take a root, you have actually the same number of roots. You know, for a smooth curve, you have L to the power of 2g roots every time you have a line bundle which has a convenient degree. Now, this happens also for those curves. Okay? All the time, you have L to the power of 2g roots, and let me just say in which sense more precisely. Yes, so this time I'm treating all possible variants of all sort, and I'm not going to enlarge this notation anymore. So nice fancy letter, multi-index here. And this is the space which consists of curves with markings, and I may call this marking sigma, which evokes more the idea of sub schemes in general. But anyway. And now I'm saying that this goes to omega log of C power S. And the interesting cases I'm thinking of are the cases where S is an integer above 0, and L is an integer above 1. So all those things are needed to set up what Witten wants, which is this Landau-Ginzburg model, as it is now usually called. But if time permits, I will tell you exactly what Witten says in a paper of his. So let me just say one more thing. We discussed multiplicities. Well, I want that Mi is the multiplicity of L at sigma I for all I going from 1 to n. And the generalization of the claim that I had yesterday is, okay, let me put a bar because this is going to be compact, and this is actually a proper unramified cover, finite is obviously proper, so finite and ramified cover of this. So you can actually look at this as a stack of dimension 3g minus 3 plus n, which is, according to my convention in this course, of degree 2g minus L to the power of 2g, just as the smooth ones are. Okay, so a little, yes.
The one from yesterday, what would it correspond to?
Right. So yesterday we spoke about two-level curves, and we noted them like so, and it would be my notation, this, but with zeros everywhere. So yesterday, today.
Sorry, so question. So when you write the upper board, the middle one, and the top line, when you write twisted by pi divided by number of homological.
Right.
What do you mean by twisted by pi? You mean the pi?
Yeah, you are thinking, or yes. So I mean that pi is the morphism spec k or c inside my curve. Now we agree, and actually it is a point that can confuse some people. So instead, what one may actually choose to speak about is a substack, which already weighs that much. And I have taken a choice, which is probably, made a choice, which is probably
I just want to make sure.
Yes, that's correct. Okay, let's have a little remark. I told you that there's 3g minus 3n plus n dimensional, but of course, let me remark that this is not true, because it is true only if some degree conditions are applied. So it's different. Okay, let me erase this. This may be even empty. So it's non-empty if and only if this equation holds. And in that case, it is a smooth the Riemann-Perl orbifold of dimension 3g minus 3 plus n, and it admits a nice topological stratification, just as in the case of stable curves, with the difference that these strata are not just dual graph. The strata are not just dual graph, but dual graph with this decoration of a multiplicity, which is chosen in the way I said. Look, this time when you are changing this thing and you're leaving smooth trivial line bundle, then delta of m is not necessarily 0. It's something else. I'll let you discover that on my notes or on your own. Probably on your own is more fun. Okay, so now I'm ready to give a big diagram which puts all these things together, i.e., well, the stack we just defined, and, well, some universal curve, which has these stabilizers and the marking, and some universal line bundle, which, as long as we keep on writing fancy letters, exists as a line bundle on a universal curve. And then as a then I'm writing these substacks. What are those substacks? These are specifying for I going from 1 to n, where the markings are inside of the universal curve. Okay? And you may actually say, but why didn't you write as usually people do sections? Well, there is a subtlety here. The thing is that those substacks, as YP pointed out, are not defined by a single map from the base to here, but I need also to lift this base, and this is something that is a fibration, a very simple one, of type locally isomorphic to this very simple map. But you have to live with that. Okay? So in order to say things correctly, I prefer to say that they have some thing that looks very much like this thing, up to adding stabilizers everywhere, and then it injects inside C. Okay? Of course, this is made precise in the notes, and if not in the notes, in some reference. There is a nice paper of Cadman that actually describes what these things are. Okay, so, but what we care for most is the singular locus of this. Which is just the locus where the node happened to be. Again, this is a substack. But now, in order to set up my definition, I want to do something. Every time I look at a point in the singular locus, I want to look to distinguish 2 points. So this is a two-folded cover, 2 to 1, which produces this cover that that associates to each node the two branches. So I'm looking at the two branches, and here I'm parameterizing not quite the nodes, but the branch of each node. Since there are two branches, I have a two-folded cover of this singular locus. The reason why I'm doing this is very clear, and it comes from the question of Motohiko. Which branch are you choosing to define your multiplicities? If I don't do this, I do not have my definitions. I cannot set up my definitions. And now that I have done this, I have a disjoint union, a nice decomposition of this. Into disjoint loci parameterized by n, the multiplicity at the node. And now I can compose this locus here, and for each m, I have a jm, which goes down to my stack. Okay, that's a lot of information, and happens to be on a blackboard that is going to disappear, so it's not going to disappear. I'm going to take my time to erase this and wait for questions.
What does R come from?
This is R.
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 Space.
Oh! So this is a notation that occurs for prime varieties, and when I started talking to Gabriel, we picked up that letter. Some people use S, which is a spin, and now, as you will see, some people use W. But this is a slightly different thing. It is associated to a Landau-Ginzburg potential, and I'm going to use W. But just the building blocks of that modular space attached to W is going to be my R. And then I'm going to play with them and produce the modular space that is attached to the Landau-Ginzburg story. So, yes, it's time to state a theorem. Which you can find in the reference 2008. So, oh, yes, there is one thing that has been mentioned. I'm considering this thing. Consider this may be regarded as an alternate sum of sheaves and as such it is a class in K theory. But sometimes, as we will see, and in all the cases we are really interested in, this is actually a vector bundle. But anyway, so it exists as a class in K theory. And now, as such, I can compute the Chern character. So the Chern character is something that is in even cohomology and exists in degree is a sum. I will express this Chern character as follows. Yes, sorry, I'm really sorry. Yes. Thank you very much. Okay, so let me just then tell you what is the Chern character of this. Well, Bernoulli polynomials. Have I defined them somewhere in the notes? I think so. So there are some numbers which are called Bernoulli polynomials, And they are very simple things. Rahul has already used them. So you take this function and you give and you expand it. And then you can do it by using polynomials. So those are polynomials. And now I'm going to, after using, actually, there is a nice combinatorics for this polynomial. So you can actually deduce them nicely from from binomial numbers. So it's not so hard. And they happen all the time in this kind of computations. So okay, we have VH plus 1 S over L pi lower star of psi H plus 1 H plus 1. You may have recognized the kappa class from last week. If not, we're going to come back on that later. Oops. And then I have an extra term, which is too beautiful to contract it over there. It is a 1 over 2 factor on top because it's the price we pay for having done this thing. Yep, so thank you very much. And then okay. So this is a formula which may look long, but at the same time very democratic, as has been said in some previous lectures, with respect to the psi classes. It can be proven in some formalism by Giventhal that this formula does something very equal to all the psi classes involved. Let's see what are the psi classes that are actually involved. So you have already encountered those guys. They are psi classes whose Poincaré dual can be seen as a cycle inside of this moduli space. Now you have seen them from usual moduli space of curves, but they're just a pullback of those. And now what you may wonder about is how I can speak about psi classes on this thing. But it is actually something that has been already discussed in the previous lectures, that the universal curves is very often equal to one of those moduli spaces. There is indeed a formula like that. And you want to know it? No. But yes.
I think there's a typo there. So H plus 1, the first before H plus 1 should have be n plus 1 to H plus 1.
Oh, n plus 1. Sorry.
You want that to be kappa class, right? So
Oh, this one.
Yeah, n plus 1, right?
Oh, yes. Thank you. Yeah, and this is what I was discussing, but with the typo was probably completely was not making sense. Now that I fixed that typo, we can have a break of 5 minutes. You recover from this shock. now you see in this formula this is psi n plus 1. What is the n plus 1 point? it doesn't make much sense. So far we have discussed of n margins. In fact, if I look at this curve here as I can write down isomorphisms like this. And something like this. I'll let you check. So just to point out to you, this is it can be S, it can be 0. It can be 0 for level curves. This should match this thing. Anyway, now it makes sense to say that there is a cycle which is Poincare dual to this and lies on this. And if I take h plus 1 powers of this and I push forward, I still get a class which is in the Chow ring of degree h. And what else? Well, there are cycles also on this guy. Okay, so there are 2 line bundles on this because each point is attached to a node and to a branch sticking out of the node. And along this branch, we have a cotangent line, and we can take the first Chern class. Those can actually be regarded as the psi classes of moduli spaces of curves in turn. So just this is not hard to figure out, and it is actually said sometimes in chapter 1.
So that's just psi there.
Right. This is the psi and psi prime, which I forgot, are those psi. Okay.
I think you didn't say what is S.
S is just a number which I fixed in the beginning, and it should be anything like this. Have you got any objection to that? It's the same as it's here? Well, yes, I did, but maybe yes. Yes, it's fine. So what I said, so how did I define it? S was when I said, okay, we're leaving this level structure story and we're enhancing it to extract roots of Omegalog power S. And you can do so. I was just wondering if there was something more subtle to your question, but there isn't. I mean, there is some. But it's actually correct. Okay. So how using this formula? How to use this formula? One way to use it is not to hide it. So maybe let's keep it there and erase here. This picture probably has been used enough. But this formula should be kept, I suppose. So consider this moduli space as one of those moduli spaces occurring in all those courses such as that of Davish-Malik, for example. And this is what is going to happen tomorrow, where it is going to have some obstruction theory, and we're going to extract some information from it. And precisely as in the previous lecture, what we have to do is to find a way of extracting a virtual class from this k-theoretical push forward or a derived category push forward. So in fact, what very often happens is that we have very complicated constructions, but then when it comes to really using them, we restrict to well-behaved cases. So let me just give one of those. So remark, if G is equal to 0, and if all the Mi are strictly positive, and s is equal to 1. It's just a special case, but actually a case that we really care for, and we will really care for in the next lecture. Then, well, R1 p lower star of L is locally free. And R0 p lower star of L, i.e. the direct image as a sheaf, vanishes. Okay, this is something that you can prove. And how do you prove it? You choose any fiber, and you see by degree reasons that for degree reasons, something is negative. You can start from a smooth fiber, and you see that the degree of the line bundle there is negative. And then you can start from going to reducible fibers. There may be something positive, but in the end, by an induction argument, you actually manage to prove that all the times H0 is 0, and that you have, by base change, these two conditions. R1 p lower star is a locally free sheaf, which I'm going to treat as a vector bundle. And now I can actually say that I want to compute the Chern classes of this vector bundle. What does this mean? Well, when I have a vector bundle, then I can take all the Chern classes and sum them up. And I want to do that. And I claim that this can be done from the Chern characters. This is obviously very well known. We know that the Chern characters are just equivalent information to Chern classes. But let me just see if, okay, so it's very easy to, once you know this formula, to try and prove it. So for this, you will need to do it in general for any line vector bundle. And no. Okay, so yeah, what I meant there is this. Oh, and I mean here this. Okay, this is actually the virtual cycle. The top dimensional thing here, C top, is the virtual cycle for the Landau-Ginzburg model. So as an exercise, try to convince yourself that this is the correct formula. You may find a mistaken sign, but I don't think so. And one very simple way to realize that this, to understand how to prove this, is to understand that both sides of this equality split in the same way when you give them sums of vector bundles. They both split as the product. So why don't you just express your vector bundle as a sum of line bundle, and then you prove it for them, and then it's gonna be easy. Okay, so as I expected, I have some time to, this kind of rigid mathematical framework is very nice, I think, but also we probably missed the confusion of mirror symmetry now, and probably it's nice to sort of bring it back. Okay, so I'll do that by telling you this short paragraph in a paper by Witten, which actually tells us how to make sense of this global mirror symmetry picture. So remember that yesterday there was a mirror, and I mentioned without writing it, but I had some questions about that, that the mirror exchanges A model and B model. So, namely H11 of this, for example, and H21 of this. But at a more at a less elementary level, we can actually interpret the exchange of these two quantities as something else. A projective line parameterized by psi with two special points at psi equals 0 and psi equal infinity, and around both of them, by using the odd cohomology of that family of Calabi-Yau orbifolds, we set up two four-dimensional vector bundles with flat connection. It was the Gauss-Manning connection in both sides. And then we said that Gieventhal and Yau have established on a punctured disk an isomorphism between a neighborhood of a punctured neighborhood of infinity and the punctured disk, which preserves another four-dimensional vector bundle, let me call it W0 if you want, with another connection which comes from Dubrovin and embodies Gromov Witten theories. And now the natural question was that this is clearly an incomplete picture, and there should be some transition which will lead us to identify some theory, enumerative theory of curves, which is mirrored to this. And this is the work of Yongbin Ruan and myself, which has been then generalized and explained in a different categorical way by Hiroshi Eritani and myself. There was going to be a talk next week. And here I have time to say something more about this question. So what is this transition between Gromov Witten theory and another theory? And I say it here because it is a nice story, and even if it comes from Witten, as it happens many times in papers of Witten, it is explained in purely mathematical terms. This is a geometric invariant theory story. So let's give ourselves a geometric invariant theory problem. So what I want to do here is to consider a Calabi-Yau. My Calabi-Yau is going to be the vanishing locus of W inside a weighted projective space of weight W1, Wn. And this has degree d. And as you know, at least in the case of homogeneous spaces, this is Calabi-Yau as long as d is equal to the sum of the weights, which is the same as saying that in a projective space with n homogeneous coordinates, I need the hypersurface to have degree n. Okay, so let's throw this number in this picture. And what I'm going to do is to act on this affine space by C star, and the weights are going to be the following. W1, W2, Wn for the first n weights, and minus d for the last one. And now, as you notice, the sum of the weights is 0. But the fact that I have introduced the negative weights poses a problem. So let's write it explicitly. The problem is that there exist non-closed orbits. And if I have non-closed orbits, I cannot speak about the quotient space in geometric in a geometric sense, because I cannot have points representing those orbits such that the pre-image is each of those orbits. So I cannot have a quotient space parameterizing the orbits. So the solution to this, which GIT provides, is to look for all open sets omega inside of this Cn cross C, which are C star invariant and such that orbits are closed. So that omega mod C star will be a separated stack if I want to keep. Otherwise, that's precisely what the problem was, right? I mean, if I allow all these non-closed orbits, then I have no chance to get such a thing. Okay, so it turns out that the GIT actually gives us a machinery for finding all these open things, open subschemes. And it tells us that the machinery classifying those depends on a polarization. You can choose a line bundle on this space, which is linearized by C star. And depending on whether this linearization is positive or negative, you have two possibilities. So one is to impose that this is different from 0, where I named x1, x2, xn the first n variables. And then since the last one plays a different role, I name it by p, and I say that p should be different from 0. Okay. So once I have those two restrictions, those are the only two that satisfy those properties. And I can actually pass to the quotient and consider these two stacks. And okay, if I want to capture the information of this hypersurface, I should add to my picture something more, a C star invariant map, which physicists easily find that it's just W times P. Since C star acts on P by lambda power minus D, and this is quasi-homogeneous, this is going to be C star invariant. So this is actually a map that should be defined on this quotient, and so it descends to a map here. Let's call this W bar. So now notice that we are dealing with two geometric objects. They look like stacks equipped with a morphism. And this morphism is what is alluded to in the title of Junli as a cosection, if I understand it correctly. So, or at least it will yield a cosection in the construction of the versal cycle. And now, let's see what these stacks are, because they are quite easy to understand. So one is just, well, omega 1 is a affine space to which we have taken off a point times C. So it's a line bundle on something, on a punctured affine space. So this is going to be a line bundle on a weighted projective space. And which line bundle? Well, O minus D. I don't know if this, let me take off this. So it's a line bundle of degree minus D on the weighted projective stack, if you allow me to call it like this, PW. It's just. And when you look at this map, you may start wondering if this is something you knew already. Well, in fact, indeed it is the composite of the natural map to O and the projection to C when I work at the level of total spaces. Okay, so I have a total space of the trivial line bundle. It is a product, so I can send it to the fiber. Okay, so we know everything about that map, and we want to know everything about this one too. Well, we can at least simplify it slightly. Notice that every fiber, every orbit, contains a representative of the form x1, x2, xn, comma 1. You can always bring p to 1. You can always renormalize it by this action. So why not reducing the action to an action on Cn? Now, it's not anymore a cis-star action because you identified many things in the fibers, but it's an action of the subgroup ZD. And now, since you have renormalized all orbits to setting p equal 1, this is just your initial W. So here we are considering the ZD equivariant map on the affine space, defining our hypersurface up to ZD equivariance. And here we should find the Calabi-Yau hypersurface. So let me see how I get to the Calabi-Yau hypersurface. I'm almost there. Well, I want to have a simple cohomology computation. Showing you that we are actually considering the cohomology of our hypersurface. Well, consider we have two spaces, right? We have one thing mapping to C, okay? So our things looks like those, and in order to give a cohomological invariant, one natural thing is to consider this O minus D over PW, comma, relative to the fiber over 1. I choose 1. I could choose any point different from 0. Maybe you prefer to choose T. Or anyway, let's keep it simple. Okay, 1. Just my favorite number different from 0. So now, if I have a stack, I should always consider the suitable cohomology. And now notice that, well, any line bundle retracts to its base. This is easy. But it's a little bit less easy to understand this variety. This is a substack of a total space of a line bundle. It, in fact, retracts to the complementary of XW. And now you can set, there is an isomorphism called the Thom isomorphism that tells you that this is nothing but the cohomology of XW itself. There is a shift in degree by 2, but that's the end of the story. So at least from the cohomological level, I have understood precisely that here on this right-hand side, I'm really looking at this stuff that I have said yesterday. And now you can play the same game here. And actually, it is a much easier game to play. It is actually very simple cohomology invariance. You're going to be reduced to study the cohomology of what is usually called the Milnor fiber. And for that, you have an algebraic tool, which is the Milnor ring. And this is going to be giving you exactly the same Hodge diagram. So this is very strong evidence that at the level of cohomology, everything works fine. Not very strong evidence. It's some evidence pointing in one direction and telling us that we should lift this theory to some theory involving curves, as people say, an A model theory, which doesn't only compute these numbers, but actually shows that when we're speaking about this, we're speaking about some quantum theory of this. So this transition reproduces this transition here. So usually people call this side the Calabi-Yau side. And this side has been commonly called Landau-Ginzburg side, which is a combination of names that often happens for singularity theory, because as I have explained, this is a singularity theory computation involving the Milnor fiber, and maybe I should just erase this blackboard and say precisely in terms of Chen-Ruan cohomology, what is this? So it's going to be work done for tomorrow. Okay, so formally, I want to study this. A stack acted on by a cyclic group. Let's have a look at what it looks like. Well, the generator is going to be a matrix e to the power of 2 pi I w1 over d dot 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 e to the power of 2 pi I wn over d, or if you prefer. Okay, and but now remember how Chen-Ruan cohomology was defined. That's a direct sum over elements of the stabilizer there. And now every time I'm playing this game of considering the fixed locus, so inside Cn, I have to consider, remember that yesterday the fixed locus was defined like this. I had a space with a G action, and then this was the fixed locus, G fixed locus. So let me use this slightly ambiguous notation, and remember that we were extracting G invariant terms. And now I'm going to tell you that these things are, well, I'm just recalling how one can compute all those things look like affine spaces. Every time you fix a G, you're just specifying a coordinate subspace. Okay? So every time you have this thing, and W is a non-degenerate polynomial, meaning that something that ends up defining a smooth Calabi-Yau here. So I should always say that W is smooth. Smooth means that if I look at W as a map, as a polynomial, it has only one singularity. The origin. Yes, yes. So it defines a smooth orbital, but it's a non-degenerate thing. That's good. And now, for all those things, we have this expression. Just consider the ring of polynomials and those variables, mod the Jacobi ideal. So suppose that the variables are any number of variables, h, and then okay, with this recipe, you can compute all this stuff, and this is going to give you those numbers if you look carefully. And what is very good about this from a conceptual point of view is that, okay, so suppose that your W is expressed as a sum of two W's, and involving two separate set of variables, x1, x2, x3, and x4, x5. For example, in our case, we always start from a Fermat polynomial, which actually is a sum of disjoint monomials. Okay? Then there are theorems of type Thom-Sebastiani that tell us how to recover that thing for W from that same thing from W for W1 and W2. This is one of the elements that makes us very confident that we can say things on this right-hand side, on your left-hand side, that we could not say for varieties. I mean, think about it. Could you do such a thing when you had an equation of a Calabi-Yau expressed as a sum of monomials? So you cannot really reproduce your variety from products of variety defined by every single monomial. This doesn't make sense. These are empty spaces, and I don't know any way of making sense of this. Whereas here I do, and and there are other things. You see, mirror symmetry has been defined for Calabi-Yau in Calabi-Yau situations. Well, it turns out then when you do this kind of operation, you use the Calabi-Yau property. You lose the Calabi-Yau property. Yet, it has been found that on this side, mirror symmetry still exists, makes sense, and is even a very simple statement. So, factoring in this way allows you to prove theorems in full generality, theorems such as the one that I've started from yesterday. And so, so if you still haven't found who is the mirror of the variety X mod the group of order 5 generated by G1, then you can use this, and maybe we'll be more lucky. Okay, thank you very much.